So I don't forget. So we'll look at this linear system, and what I'm trying to do, the side note here is more of just sort of anticipating in the old 17C book, after we studied how to solve these things, they did a unit on sort of interpreting the differential equations in terms of what they could represent, particularly with for lack of a better term, species interactions with each other, right? We talked about a predator-prey situation on one last week, and I think on Friday we talked about one that could have represented commensalism. So trying to show you some different scenarios. But again, this part here, I haven't seen anybody talking about that yet, but that could be coming. So might as well talk about it while we're solving these anyhow. Okay, so dx dt equals negative 2x plus y, dy dt is 2x minus 3y. Linear systems, because our biggest power of x and y are both 1. We don't have any squared terms. I know some classes we're talking about the difference between a linear system and a non-linear system, where you might have a power like x squared or something like that. That would be non-linear. I've also heard the terms autonomous and non-autonomous discussed. Recall from 17b, autonomous just means, so we're talking about the rate of growth of x over time, and same thing for y, but notice our differential equation has nothing to do with time. It has to do with the populations of x and y. That's what we mean by autonomous. So I could call this autonomous linear system. As opposed to non-autonomous, what you would see is there would be a t in your equations. You might have 2xy minus 3y plus t or something like that, in which case you're saying that your growth rate of y would be a function of t as well. So now I haven't really mentioned that because in the big picture, we're really not going to be concerned with anything that's non-autonomous. The ones we really focus on are the autonomous differential equations. So, okay. So just the side note of this thing, in this particular linear system, if we thought of x and y representing populations of, say, 2 species, then one thing we could note about this is that the rate of growth of x without y, it's going to decline, right? That's a negative thing, but y has a positive effect. So whatever y represents, it's helping x grow, right? And same thing for y. Without x, y has negative 3y, y would decline, but the presence of x is benefiting y, right? That's a positive 2x. So when this happens, when 2 species have the effect of benefiting each other, that's called mutualism. Some of you probably know this. Or symbiosis. Oops, I can't spell it though. S-Y-M-B-I-O-S. Okay. And a good example of that, plants and pollinators, right? Plants need bees and other pollinators to spread the growth so that they can develop new plants, and of course the bees depend on the plants for food, right, for pollen. Okay, so let's get to the math now. So we'll run through this a little bit quicker. This is our 3rd one we've done together. So the matrix form for this, we could write this as dx bar, recall dt, that captures both of those, is equal to, we can take the coefficients, -2, 1, 2, -3. We can even write x bar here, or just to really be clear here, let's make this xy. And we know that for our solution, we're going to need the eigenvalues of our matrix A there. So take a second, find the two eigenvalues for that matrix. We're going to need the determinant of A minus lambda I to equal 0. So that's going to give us -2 minus lambda, -3 minus lambda, minus 2. And what I usually do on these, if I'm foiling it out, I know I'm anticipating a quadratic. So I want to have my lambda squared first. So I actually foil backwards. I do the negative lambda times the negative lambda is lambda squared. This times this, there's a positive 2 lambda plus a 3 lambda. So that gives me plus 5 lambda. And then I get a negative, nope, that's a positive 6. There we go. This is a positive 6, and then I know I'm going to have a minus 2 here, so that would be plus 4 when everybody's combined. And this factors nicely. Plus 1, plus 4. So I get my two eigenvalues of -1 and -4. Okay, then we're going to need the two eigenvectors that go with those two eigenvalues. So that would probably be the next thing to go for. So for lambda, let's call lambda 1 is -1. We're going to do matrix times eigenvector that we're looking for is equal to eigenvalue times eigenvector. So we have -2, 1, 2, -3 times the vector xy equals -1 xy. Multiplying out the first row, -2x plus y equals -x. That's the top number. And knowing that all I need is a relationship between x and y, I think I've got it here. If I add the 2x over to the other side, that tells me y equals x, which tells me the condition for my eigenvector, whatever x is, y should be the same, right? This is the relationship. So the best thing to choose, I think, for x, with a logical thing to choose, would be choose x equals 1, in which case y is going to be 1. All right. Here, choose x to equal 1. Pull this back. So try the other eigenvector for lambda equals -4. See what you get for that one. So here, if I move the 2x over, I'm going to get y equals negative 2x. Yeah. Which tells me then that's the relationship between y and x. So if I choose x to be 1, that means y is going to be negative 2. Okay, and once we have our eigenvectors, we're ready to write our general solution. We don't have any initial conditions, so this is as far as we're going to take this one. Remember, our general solution can be written in vector form: x of t, x bar of t, c1 e to the lambda 1 t times the eigenvector associated with lambda 1 plus c2 e to the lambda 2 t times its eigenvector. So what we would have, c1e, our lambda 1 was negative t times the vector 1, 1, c2 e to the negative 4t times the vector 1, negative 2. And it's fine to leave your solution this way. This is kind of the more condensed way. But recall, this is really talking about two solutions, right? X bar stands for X and Y. Okay, this is really, here, we'll write it right here. This is really X of t and Y of t. Okay, so then, yeah, of course, if we had initial conditions, we could solve for the constant C1 and C2. But in terms of like the long-term behavior, which leads us to the stability classification, it really isn't so much about the constants, it's about what happens here, right? What happens to, over a long period of time, what's going to happen to the e to the negative t? And when I say a long period of time, of course, I mean t going to infinity. What's going to happen to both this and this if t goes to infinity? Let me make a note here. For the stability classification, recall the equilibrium for this linear system, where you would set dx dt, which was, what was it? It was negative 2x plus y equal to 0, and dy dt, which was 2x minus 3y equal to 0. The only solution that's going to solve a, okay, here's another term, homogeneous linear system. Homogeneous just means all you have is an x and a y. You don't have an additional number hanging out there. We talked about that, I think, on Friday's video. The equilibrium is always going to be 0, 0. That's the only number that will solve both of these equations equal to 0. So by stability, right, what we want to know is what happens in this solution as t goes to infinity. Will we go to 0, 0, or will we go away from 0, 0, right? We'll say, what happens to x of t and y of t as t approaches infinity? And there's a little bit more to that. It's also, we want to know how does it go, how does it, the solution look? You know, does it, as we saw, the two classifications we've looked at in previous classes is we've done a source and a saddle, and both of those are unstable. They go away from the origin, but it's how they go away, right? So we're also interested in how the solution looks, but that's part of the stability thing, right? So clearly here, right, if we took the limit as t went to infinity for x of t, which is the c1 e to the negative t, you would read the top part of your vectors times 1 plus c2 e to the negative 4t also times 1. As t goes to infinity, we know this term is going to go to 0. This term's going to go to 0, which means my solution for x of t is going to eventually have to go to 0. And the same thing's going to be true for y. Because you have, right, because we have e to the negative infinity, that's the same thing as 1 over e to the infinity will approach 0. And that's what's happening for all of these. This is going to go to 0. This is going to go to 0. So we'll get 0 for that. So the classification for this, we're going to call this, this is a, so 0, 0, our equilibrium 0, 0 is called a stable node or a sink. Okay, and I'll talk about what we mean by sink when we look at the phase plane, which is what's coming next. Stable, though, just means, right, if my initial condition, if my starting value for x and y was something other than 0, 0, I can tell by this that eventually over time, both x and y would go back to 0, 0, right? So it's stable. And perhaps you can see, now we're going to start to look at this. What really made it stable was the fact that these guys went to 0. And why did those go to 0? It goes all the way back to your eigenvalues, right? The reason this goes to 0 is this was a -1. That was my eigenvalue there, and my eigenvalue there is -4. And if they're both negative, you can tell by the solution that the solution is always going to go to 0, right? You're going to have e to the negative infinity. Okay, I said I was going to spend a little more time talking about the phase plane, so I better get to it here. It's unclear in class to me, unless you've heard something different, whether you will have to be able to generate your own phase plane. Yes. Thanks, I can mix those. Whether you will have to generate your own phase plane, or what I have seen in some people's homework is you get a basically a problem, and you have to match up with the you have to match it up with the phase plane. There's like, multiple choice. Could it be this phase plane or this phase plane? And that's a little bit easier, but you still need to know something about how the phase plane was constructed. So I don't know that you'll necessarily have to generate your own phase plane, but we still get something out of this. Okay, can I pull this away now? Yeah, okay. Okay, so we're going to sketch a phase plane with the Eigen Lines. That's part of it. We did a little bit of this on Friday. And also talking about the null-clines, which I did talk about on Friday, but I wanted to spend a little more time on those. And then we're going to sketch possible solution trajectories for initial conditions. Yeah, I saw this in the book. I was writing my initial conditions as like x of 0 equals 1, y of 0 equals 6, but it could also be written like this as a vector. That's how some of them are written in the book. So the x subscript 0 means time is 0. This is when t is 0. And same thing here. Oops, I need to get it out. Yeah. So let's talk about the null clines. We have all the we have the eigenvectors, so we can draw the eigenlines, but let's talk about the null clines. The null clines, let's start with dx dt. And if you have, okay, when we get to the graph on the next page here, I'm gonna color code this a little bit so that we can distinguish between eigenlines and null clines and stuff like that. So I don't know if you have color here, it doesn't have to be the same colors I'm using, but I'm gonna try to color code this a little bit. So one of your null clines comes from the differential equation dx dt, which is negative 2x plus y. And if I set that equal to 0, which we know 0, 0 solves that, but if we look at the equation you end up with, y equals 2x is our null cline for dx dt equals 0. And the thing to keep in mind here when we sketch our phase plane is if dx dt equals 0, right, this means all of our solution curves should, if dx dt is 0, there's no change in x. That means the only change is with respect to y. That means they should be vertical, right? Should, or how about this, have vertical tangents along this line right here, y equals 2x. Right? If there's no change in x, if dx dt equals 0, that means all of the change has to be with respect to y. The only way you can do that is if you go vertically. Similarly, my other null cline, dy dt, which was, what was our equation? 2x minus 3y. If I set that equal to 0, gives me y equals, looks like 2/3 x. And so by the same analogy here, I guess, all solutions, same logic, should, if there's no movement in the y direction, then everything has to be horizontal, right? If dy dt equals 0, then everything has to be horizontal. So all solutions should have horizontal tangents along this line. And so what a null cline is there's no change. The null means no, cline is kind of like incline. Incline is like a slope. No slope, basically. There's no slope in the x direction along this line. The other term for it, I can't listen to Carlson's lectures, and I can listen to Rademacher's. I haven't tuned in a couple of days, but the other term for this, I don't know if they're calling it this, is isoclines. Isoclines, like what, right? One, no. Same as null clines. Okay, so let's get to the graph now. Try to keep that last part there, and enough of the. So draw nice big axes for x and y. I just tried to get some kind of a scale, really only in the first quadrant. So I marked out 10 units in the x and y. When we do these phase planes, we sketch the whole thing, but for application problems, I mean, if we're talking about populations of species, right, we're not going to have any negative x values or negative y values. And I mean, if we have no context, sure, we can talk about that, but I like to think about the real world applications where everything's going to happen here, right, in the first quadrant where x and y are positive. And so what we want to add to this, let's first, well, since we just talked about it, let's add our null lines. So y equals 2x was our dx dt null line, and I did that one in red. Where's my nice ruler? Y equals 2x, so that's has a slope of, goes through the origin with a slope of 2, so up 2 over 1. So through the origin, that null line should look something like this. This is y equals 2x, and that was for the null line dx dt equals 0. The other null line was y equals 2/3 x. That's a line with a slope rise over run, 2 over 3. So up 2 over 3. Whoop. Okay, so through the origin as well, that line looks something like this. And then let's also bring in our Eigen Lines. Remember, your Eigen Lines are just your extension of your two eigenvectors, which were, let's see, one eigenvector was 1, 1. So 1, 1, if you plot that vector, you just go over 1, up 1. So that's basically in the same direction as y equals x. So this is basically, I'm just going to write this. This comes from the eigenvector 1, 1, which was associated with the eigenvalue -1. And then the final one was 1, -2. That eigenvector goes 1, -2 you go over 1, down 2. So I guess I'll need a right here. Close enough. All of these lines actually tell us something about how the solution looks. So let's start with the Eigen Lines, okay? So as we saw, the eigenvalues being negative, right? In the general solution, the eigenvalues being negative had the result of bringing the solution back to 0, right? The fact that both of these were negative made x of t and y of t go back to 0. So in terms of, okay, you've seen a phase plane, right? Those little arrows are vectors, or you could think of them as tangent lines to the solution, to some solution. Any eigenline that comes from a negative eigenvalue can be thought of as that's like the direct route back towards the origin. We know this is associated with stability, so it's going to take us back to the origin. Your arrows will go inward. So same thing with the -4. Solutions will go inward. And so we're getting a bunch of, right, that the direction fields that I was showing you, the phase plots, phase planes, you know, they take a lot of time to unless you had a computer generated one, but look, we're getting a lot of information just from that. Now, the thing we said about the null lines, and we said that along dx dt, if dx dt is equal to 0, that means there has to be vertical, right? We said the solution had to cross vertical tangents. And so what that means is everywhere along this line, you know, if I were to sketch a solution curve, it's going to cross this line in a vertical way. So you can put, it's typical to put a bunch of little vertical lines, okay, along this null line. Now, I don't have arrows attached to them yet because although I think I know which direction these would go, right? Because if it has to get back to here, they're not going to be going outward. They're going to be coming this way, right? They're going to be going towards the origin, but we'll confirm that in a second. And then similarly for the dy dt equal to 0, which we said was going to have horizontal tangents, everywhere a solution crosses this null line, it would cross horizontally. So we'd have a bunch of horizontal lines on this. Make those darker. The green doesn't show up as well, I'm noticing. Okay. So yeah, the Eigen lines just come from setting the equations equal to 0. Where was that? No. Yeah. Just taking your original, oh, I got it right here. Just taking your original differential equations and setting them equal to 0. So if you set that equal to 0, you get y equals 2x. And then I'm just plotting that. That's a line through the origin. These don't have to be perfect, right? Yeah, exactly, Milan. If the eigenvalues are negative, it's going to be stable. Now, as far as sketching solutions, we posed on the previous page, what would a solution look like if it was starting value was 1, 6? So if we locate that point, 1, 6, 1, 2, 3, 4, 5, 6, right here somewhere. Okay, so here's our initial condition, 1, 6, initial condition. Now I know that this solution, because I know the stability is stable, it has to come back to the origin. But sometimes it doesn't necessarily take a direct route. Like it might go this way first, it might go this way first. And sometimes we want to know that. So one thing, before I draw the solution at 1, 6, here's another thing you can do. You can find the initial direction of your solution by plugging the point 1, 6 into your differential equation. So for example, dx dt was negative 2x plus y. If I plug in 1 for x and 6 for y, I'm going to get negative 2 times 1 plus 6 gives me positive 4. And dy dt had the differential equation 2x minus 3y. 2 times 1 minus 3 times 6. 2 minus 18 gives me negative 16. So what this tells me, if I put this together, you can think of this as a vector. Think of this as a vector for negative 16. How does that vector look? How does this vector look? Remember how you plot vectors? This is x, this is y. So that'd be a vector that goes over 4 units in the x direction and down negative 16 in the y direction. So the vector itself would kind of look like this, right? This would be the vector. So what that tells me then, is everybody clear on this part right here? I'm just plugging in my initial condition into my differential equation to kind of get an initial direction of motion. So what you would do for negative 16, keep that vector in mind. That means my initial motion here is, it's going a little bit to the right and down, right? It's going off at an angle down, but a little bit to the right. So my solution back here doesn't go straight to the origin. It's going to actually go this way, right? A little bit down, a little bit to the right. Just like that vector. Now, we can tell what's going to happen. we know it has to get back down to 0. So this solution is going to come through here. Now, what happens when it crosses the null line? Remember, this line has to cross vertically, right? So I can tell my solution is going to cross vertically here and then get pulled in, and eventually it has to go to 0. I can draw little arrows here. Has to cross this vertically. Do I have another color? Let's see. Put here. Crosses vertical. Right there. And every solution, if we had different initial conditions, what you would expect is they would cross vertically here, you know, different initial conditions. Now, what about, there was one other initial condition, which I think was 8-2. 8-2 is like up here somewhere. And we want to know, how does this solution look? We know because it's a stable node that it has to go this way. And, oops. Once again, we want to know, how does it go? Does it go straight there? Does it go underneath? Does it go up a little first? So we might want to know what the initial direction of the solution is. And we can do that once again by just plugging into the differential equation. So for 8-2, it's the same differential equations. Well, not that one's not that. It's the same one up there. So it'd be -2 times 8 plus 2 is -16. That's -14. dy dt is 2x minus 3y. 2 times 8 minus 3 times 2. 16 minus 6 gives me 10. What does that look like as a vector? -14, 10. That would be a vector that goes to the left, right? -14 and up 10. This is x, this is y. So the vector itself would be going to the left and upward, right? Left and upward is this vector. So back on my graph, I can almost, if I zoom it out a little, there we go. Back on my graph, that tells me from 8-2, my initial motion is going to be, you know, it doesn't have to be perfect. It's going to be kind of going in this direction, isn't it? That's my initial motion of my solution. Now, it does have to get to here, but just like the other one, when it crosses this null line, this time it has to be horizontal, right? It must be horizontal there, and then it's going to come inward and approach the equilibrium 0, 0. The blue lines are your Eigen lines. Those are just an extension of your vectors. Just plot your vector like this. The one right here was 1, 1 was my eigenvector, and I just extend that, okay? And they kind of act like asymptotes. They really do. Your solutions will never really cross them. When they get close to it, they're going to approach it like an asymptote. So this solution, this is what my solution would look like. How do you determine the arrows on the Eigen lines? It depends on which Eigen line. Oh, the Eigen line. Yeah, the Eigen lines. Any Eigen line that's coming from a negative eigenvalue, I should write that in. Let's see. Arrows on Eigen lines from negative lambdas point inward. They're going to take you back to 0, 0. And then, of course, if they came from a positive eigenvalue, they'll go outward. Okay, and I've got a summary for this on my next page here. We'll summarize all of this. Oh yeah, one thing here too, you can see how all the solutions would kind of come inward. And so I think this is where that name, you know, we called we called this a stable node. We also called it a sink, right? And I think that name, I mean, if you've ever, right, you know, when your sink is full of water and it all drains, right? All the water flow is going to this, or so it kind of, to me, it's kind of an appropriate term for what the solution looks like, right? Everything is flowing inward to this 0, 0. So it kind of looks like a sink that's draining. Okay. So there's a pretty detailed phase plane. Like I said, I don't know if you're going to be asked to do that much in detail, but and to graph this yourself. But I think if you're asked to pick out of a lineup a possible phase plane for a, you know, a set of differential equations, and you've got multiple choices, some of these ideas can help you, right? Like you could look at the well, definitely the eigenvalues and the eigenlines, right? But even so, you know, you could have sinks. I could come up with another linear system that is a sink as well, that has your two eigenvectors, but maybe this one is the null-Klein where the solutions are vertical, and this is the one where it's horizontal, right? Maybe, because it all depends on the equations. So understanding how the null-Kleins work, I think, is also a skill, and also understanding how to find a direction at any given point, how your solution would move at that point by just plugging into the differential equation. I think those are important skills. But let's summarize here. And what we've covered all three of these now. Basically, what happens if you have a linear system that has real eigenvalues, then there's three classifications, and some of them we've looked at here. If your eigenvalues are both positive, oh, and I should say this real, I think I mentioned this last time. On Wednesday, we're going to look at what happens when you solve your quadratic equation and you get imaginary numbers for your eigenvalues. They actually have meaning. They actually do tell us something about the solution. But that's a little more complicated. We'll talk about that on Wednesday. But if our eigenvalues are real, then there's three possibilities. If they're both positive, and I'm just going to draw just sort of a general, what a general solution would look like. If they're both positive, you're going to have two eigen lines. Let's just call this V1. This is general, right? And V2 might look like this. They don't have to cross like this. They can actually both be in the same quadrant. I'm just drawing a general solution here. Now remember, if your eigenvalues are positive, this would be the opposite of what we just saw. That would mean along your eigenlines, your solutions are going to go away from your from the origin, because that's your equilibrium. And so if I had an initial condition, okay, I know there's null-Kleins that we don't know, but generally speaking, if I had an initial condition, let's say that put me right here, if this was my initial condition, I could tell my solution would probably get attracted to this eigenline and my solution would move away. If my solution was here, it would probably, again, approach this asymptote right there, right? So those would be what solutions would look like. And so in this situation, we would say definitely it's unstable because there's no chance for any solution to get back to 0, 0. This is an unstable node, also called a source. If both of your eigenvalues are negative, then your two eigenvectors, this is what we just saw. Let's just redraw. Let's say this is V1, V2. Your arrows point inward. And so any solution that we have, any initial condition, as we saw, it doesn't necessarily have to go straight, right? It might climb a little bit first, but then it's going to eventually go back to 0, right? Or if it was here, maybe it'll approach like this, right? And then go in. These are just hypotheticals. But every solution, no matter where you start, is going to come back to the origin. And so we already classified this. This would be a stable node, also called a sink. And then the third possibility, this was, I think, the one, I don't remember when I showed you this. I don't remember if it was Wednesday or Friday of last week. But that's where you have one eigenvalue positive and one of them being negative. So let's just assume, could be the other way around. Let's just assume that lambda 1 is positive. So this eigenvalue vector is associated with this eigenvalue. And if this was positive, we know what happens is the arrows go away if it's associated with a positive eigenvalue. And if lambda 2 was negative, and this was the eigenvalue for the eigenvector for lambda 2, these arrows would go inward. So what a general solution would look like, I'm going to start with an initial condition over here just to really capture the whole thing. If this was my initial condition, what you would see is these arrows would have the tendency to pull your solution in towards the origin. But it's like I said, these kind of act like asymptotes. Eventually, they would get pushed away, repelled, so to speak, and my solution would go away from the origin. Same thing, here. If my initial condition was here, it would get pulled in, but then eventually get pulled out, repelled from the origin. So now so in almost every situation, this would be considered unstable, right? It's going to go away from the origin. There is a scenario, right? If my initial condition happened to be right along this line, and it had to be right on that line, then yeah, your solution actually would go in to 0. It would be stable, but that's a very, very limited chance for the solution to be stable. So we generally call this unstable still. This is unstable. And we call this one a saddle. I think I've already referred to it as a saddle before. But I will note, if initial condition on the eigenline associated with the negative lambda, then it could be stable, right? It would be stable, I guess. Not could, it would be. But I had one more sheet. We can talk about this on Wednesday too. Maybe I'll start with this. What you hopefully are now starting to realize, I think some of you are, I can tell from your comments, is that the stability, once you find your two eigenvalues, which is the very first step, right, in your solution, you already know what's going to happen in terms of the stability, right? If I find out one eigenvalue is positive, one eigenvalue is negative, I already know it's going to be a saddle. The rest of the work in finding your eigenvectors and stuff is you might be asked to do it, but you already know it's going to be a saddle. And like the one we just did, if my eigenvalues are both negative, it's automatically a sink. So everything's determined by your eigenvalues, which is why they're so important. All right, everyone. I guess I'm out of time. I'll see you on Wednesday. I'm going to stop recording here.